Well, next I want to show you some notation for partial derivatives. So I'll just write down the partials with respect to x, but of course the similar notation applies to y as well. So we've seen the subscript, so f sub x means the partial derivative of f with respect to x. Sometimes we'll go ahead and say of xy at the end, same thing. You'll see this is a new symbol probably. This is the nabla symbol, so partial f, or just the partial symbol, partial f, partial x. And of course I could say partial x of f of x, y. So let's do some examples. I want to go ahead and compute partial x and partial y for this function. And so why don't you pause the video, work these out yourself, and then we'll go over them together. All right, so when I want to compute partial f, partial x, I'm realizing that I'm holding y constant in that case. And so this is just cosine, use the chain rule, cosine of x, 1 plus y, times the derivative of the inside. And this is just x times the constant, so the derivative is the constant. And so you can write this if you want as cosine of x over 1 plus y. You know what, let's just leave it. Yeah, it's good. I was going to say 1 plus y like that, but with the fraction on the inside, it's kind of messy. So we'll just, maybe we can write it like this. Somehow I like that out front. And then we'll have a cosine of x over 1 plus y, whatever. Okay, partial f, partial y is a little bit harder because now y is downstairs. Still the same starting setup. You take the derivative of the outside, which is cosine. You plug in the inside again. But now you've got to multiply by the derivative of the inside with respect to y. And of course, the way to think about it is 1 plus y to the minus 1, and there's an x there. So this derivative is going to be times minus x, right, because the negative 1 comes down, 1 plus y to the minus 2 times the derivative of the inside is just 1. And so let me erase my scribbles. And that's it. We can clean that up a little bit. And again, I'm going to move this part out front. So I'm going to write this as negative x over 1 plus y all squared times the cosine of x over 1 plus y. So those are a little bit more complicated partial derivatives. Let's look at another example. Here, for this example, we're actually going to do your favorite kind of differentiation from Calc 1. We're going to do implicit differentiation. So I can still compute partial z partial x for this equation even though I don't have z by itself. And it's exactly the same implicit differentiation that you've done before. You are assuming that z is a function of x and y implicitly. And so, for example, if we want to find partial z partial x, I'm going to get what, a 3x squared partial x. This goes away, it's nothing. Then I'm going to get a plus 3z squared times partial z partial x plus, now I've got to do the product rule because x and z are both functions of x. And so I'm going to get plus 6yz plus 6xy partial z partial x equals 0. And so now I need to solve for partial z partial x. And so let's see, we'll move this piece across the equal sign and then this and this back on the other side. And so you're going to get this partial z partial x equals, and let's see, it's going to be negative 3x squared minus 6yz. This piece and this piece go on the other side. And then we're going to move this across so it's a negative 1. So we're going to have dividing by, and it's going to be what, 3z squared plus 6xy minus 1. And I think I'm going to erase that. I don't want to do the other one. If you can do one, then you can do both. So there you go. That's partial z partial x. Finally, I want to make some observations with you that partial derivatives are themselves functions of two variables, and so they actually have partial derivatives. So you can talk about second order partials, and I've written them all down here. So the notation can be a little challenging, so let's look through this. I want to take the partial derivative with respect to x of f partial x. That's fxx, we'll call it. And you'll sometimes see it written like this as well. There's also these mixed partials where I started with f partial x, then I take partial y of that. Or I start with f partial y, then I take partial x of that. So the notation here, when I'm using the f notation, the inside thing is the thing you do first, and then the outside, the right hand, is the partial that you do next. Whereas with this notation here, it's the other way, right? Partial x and then partial y of partial x. So make sure that you realize that the order of the way it's written, the order of the symbols changes depending on the notation style that you use. And so let's just go ahead and say that all of these are referred to as second order partials. So we can compute the second order partials for this function. Let's see. So we can talk about f partial x, and we're going to get what? 3x squared plus 2xy cubed, and f partial y, and we're going to get 3x squared y squared minus 4y. Now we can talk about f partial x, which is what? 6x plus 2y cubed. I'm going to get f partial y. That's going to be 6x squared y minus 4. I can talk about f partial x partial y. So looking here, taking the derivative of this with respect to y, you're going to get just what? 6xy squared. Or we can talk about f partial y partial x. So you start with f partial y and take the partial derivative with respect to x of this, and you get what? A 6xy squared. So of course we notice that these are the same. Well, I want my highlighter, that these are the same, and that brings up an important question: are they always the same or not? And so we'll answer that in the next video. Actually, no, we're almost done. Let's answer that right now. So we'll just end here. This is going to be a shorter section. So Claro's theorem says that if f is defined on a disk D containing the point you're interested in, and both the second order partials, fxy and fyx, they're continuous on this disk. And when I say disk, I literally mean a circle around your point. So then in that case, every time f partial x partial y at the point AB will be the same as f partial y partial x at the point A comma B. Moral is, for nice functions, most of the functions we look at are going to be nice in this sense. For nice functions, the mixed second order partials are always going to be the same. And that's really handy to know, because then you don't have to compute both. You just compute one. And I'll just end with a remark. There's no reason to stop with second order partials. You can compute third order partials. You can compute f partial x partial y, or f partial x partial y partial x partial y. This thing goes as deep as you want to go. For nice functions like polynomials, these will eventually zero out, but you can imagine lots of functions where you can go as far down this rabbit hole as you want to go. So that's that. Well, let's end here. This is going to be one of the fewest videos per lecture that I think I've done, but that's okay.